So in this video we're going to be talking about some of the more real-life applications of electrochemistry. Now, you don't really have to know much about these, but a teacher wanted us to go over them, so here we are. So a real battery is just a galvanic cell or a group of galvanic cells connected together. Now, one type of battery is a lead storage battery. These are often used in cars because they can last a long time, endure a wide range of temperatures, and they don't break easily. So in this battery, the anode is lead and the cathode is lead that's coated with lead dioxide. And both of these are surrounded in a solution of sulfuric acid. So here you can see the two half reactions and then the overall reaction. And in the anode, here lead is getting oxidized from 0 to +2, and in the cathode it's getting reduced from +4 here to +2 here. Now, a typical lead storage battery has 6 cells that are connected together, and each of these cells has multiple electrodes that are in the form of grids. So here is one section of one cell. Now each of these squares is an electrode, and they're really just grids. And so these grids are surrounded in an electrolyte solution of sulfuric acid. Another type of battery is the dry cell battery. This battery is really small, so it's used for devices such as calculators or watches. Now, a fuel cell is a galvanic cell in which the reactants are continuously supplied. So in a normal galvanic cell, we have an electrode and then the electrolytes, and then once it runs, we don't do anything to it, we just let it run. But in a fuel cell, we have to continuously add the reactants. So there are many types of fuel cells, and here is an example with hydrogen and oxygen. So you can see here hydrogen and oxygen are continuously pumped into this cell. And so the hydrogen comes in and it reacts with this hydroxide here to produce water and electrons. And then the electrons flow through this wire and power whatever is in the circuit. And then they come back to this electrode over here. And then at this cathode, oxygen comes in and then it reacts with water and these electrons to produce hydroxide. And then this hydroxide can be used again in the anode reaction. And the excess water has to leave through here as steam. So corrosion is a process in which basically materials decay because of a chemical reaction with the environment. So when we talk about metals corroding, we're really talking about the oxidation of metals. Now, the reason that metals corrode so easily is because they are easily oxidized. If you look at a table of reduction potentials, most metals have a potential much less than the potential of oxygen. So if the metal and the oxygen react, the oxygen will be reduced while the metal is forced to oxidize. And this reaction usually has a very positive potential, which is why metals corrode easily. So metals often develop a coating of oxide that helps prevent further corrosion. So like the whole metal isn't just destroyed by the oxygen. Now, some metals such as gold are hard to oxidize. If you look at the table, gold actually has a positive reduction potential. So these are called noble metals because they don't easily oxidize. So here we have the corrosion of iron. Now, steel, which is mostly iron, has a lot of nonconformities on its surface. Now, due to these nonconformities, there are areas where iron is more easily oxidized, and we call these anodic regions. So you can see here there's an anodic region and a cathodic region. And then we need some moisture on the surface of the steel. So in the anodic region, since iron is more easily oxidized, it will be oxidized to produce Fe2 plus and some electrons. And then the electrons flow through the steel to the cathodic region, where they reduce the oxygen in the atmosphere. Now, the Fe2 plus that was produced in the anode reaction flows through this moisture, so the water kind of acts like a salt bridge to transport the ions. And then the Fe2 plus goes through the water to the cathodic region, where it reacts with oxygen to form rust. And rust is just a hydrated compound of iron 3 oxide. Now, one of the main ways to prevent corrosion is to apply some sort of coating, like a paint or metal plating. For example, galvanization is the process of applying a zinc coating to steel, because zinc will be oxidized before iron, as you can see from these half reaction potentials. The potential for zinc to be oxidized is much greater than the potential for iron to be oxidized. So it acts kind of like a sacrifice. It'll be oxidized before any iron will oxidize. Alloying is also used to prevent corrosion. For example, you add chromium and nickel to steel, and the chromium and nickel both produce an oxide coating that prevents oxidation. Now, electrolysis is often used to remove metals from their natural state, which is ore. So aluminum is found as aluminum oxide in the ore, bauxite. Now, it's usually difficult to reduce aluminum into solid aluminum because it has a lower reduction potential than water. So we can't use an aqueous solution, or else the water will just be reduced instead of aluminum. And aluminum also has a very high melting point, so we can't easily just use a molten compound. So the process that we use to extract pure aluminum from bauxite, we use this compound called cryolite, and when this cryolite is mixed with the aluminum oxide, it drastically reduces the melting point. So then we can more easily get the solid aluminum through reduction.